All right, today's video is about z-scores. Z-scores are standardized scores to compare different variables by standardizing the distribution. So they help us compare things that are not exactly the same because they're comparing each group to other people in that same group or other items in that same group. For example, a college admissions officer wants to determine which of the two applicants scored better. Pam, who earned an 1800 on her SAT, or Jim, who scored a 24 on his ACT. Student A responded, obviously Pam, because she scored way higher than Jim, because 1800 is way higher than 24. Student B responded, Jim scored better because the ACT is a harder test. Student C responded, you can't tell, they are different tests. So there becomes this issue where Pam took a test, Jim took a test, they are different tests, so student C is right. It matters that they're different tests. We can't go with student A and just say that obviously Pam is better because she got a higher score, because clearly they were out of different amounts. There were a different amount of total points. So what we do generally in school is we turn those scores into a percentage so that you can compare a homework assignment that was worth 10 points to another homework assignment that was worth 20. We go to a percentage. I got 9 out of 10 on one, that's a 90%. I got 17 out of 20 on the other, that's an 85%. Clearly I did better on the first assignment than the second. So percentages are one way that helps us compare when the units are different, when they're out of different amounts. So in school, we've been doing this a lot. We've been comparing things that are different. But now we're going to take a look at how we can compare different groups by standardizing the scores. So SAT scores are distributed nearly normal. So the normal distribution looks like this beautiful bell-shaped curve that has an inflection point right at one standard deviation below the mean, and another inflection point right at one standard deviation above the mean. And an inflection point means the curve changes from concave down in the middle to concave up. So it's that point where it gets pretty straight and then it switches to concave up at the end on both of the tails, and then the middle is concave down. So that's called the inflection point. So this is a normal distribution. The mean of 1500 is in the center of the normal distribution, and the standard deviation of 300 is used as the width of the tick marks on this particular graph. So the mean goes in the middle, the standard deviation is the width of each tick mark. So you can see that from 1500 to 1800 has a difference of 300, and that 300 is the standard deviation for that test. The ACT, you'll notice this other normal curve. Notice the curve looks exactly the same. The only difference is the x-axis, the horizontal axis, and it's centered at the mean of the ACT scores, which is 21. So the ACT has a mean of 21, and that's in the middle. And then you can see the width of each of these tick marks is 5. That means the standard deviation is 5, which it says right here. Pam, who earned an 1800 on her SAT, or Jim, who earned a 24 on his ACT. We can see here that Pam is right on that tick mark at 1800. Jim is in between the mean of 21 and the 26 tick mark because he earned a 24. So to answer the question of who did better, we're comparing Pam to all of the other people who have taken the SAT, and we're comparing Jim to all of the other people who have taken the SAT, and better means did better than more people that took the same test in this context. So visually, Pam looks further to the right on her distribution than Jim does, meaning that Pam did better than more people on her test than Jim did. Therefore, one could argue that Pam did better overall. The z-score particularly has an equation, a way to calculate it. The z-score for a data value is the number of standard deviations it is above or below the mean. So the z-score is measuring or counting how many standard deviations a score is away from the mean. So in order to calculate a z-score, you need to know 3 things. You need to know the observation value, so the value of Pam's score or the value of Jim's score, the mean of that particular distribution, that test or that group, and then the standard deviation. We're using SB here to represent standard deviation. Observations that go more than 2 standard deviations away from the mean, meaning their z-score is either above 2 or their z-score is less than -2, so outside of 2 standard deviations away from the mean, are considered unusual. Z-scores can be used to compare values from 2 different distributions, like we're going to see with Pam and Jim. Z-scores apply to all distributions, not just normal distributions, though that's the context that you're going to see the most frequently and first. The units of the z-score are standard deviation, so it's counting how many standard deviations away from the mean. Positive z-scores are above the mean, negative z-scores are below the mean. So to calculate Pam's z-score, here's another version of that formula. The x stands for the value, the mu stands for the mean, that's the population mean. We use x bar to mean the sample mean. If we don't have the population, we can use the sample mean. And then sigma stands for the standard deviation. We also use S of x for the sample standard deviation, and that's on the denominator here. You can see this notation. This reads, the SAT is approximately, is that squiggle, normal is the M, with a mean of 1500. The mean always goes first, and a standard deviation of 300. The standard deviation always goes second. And the ACT is approximately normal, with a mean of 21 and a standard deviation of 5. That's how you would read those symbols. Pam's score was an 1800, so we take her score minus the mean and divide the standard deviation, and we get a score of 1. Pam's z-score is positive 1. Jim's z-score is his score, 24, minus 21, divided by 5, which is equal to 0.6. So Jim has a z-score of 0.6. He scored 0.6 standard deviations above the mean, better than the average. Pam scored 1 standard deviation better than the average. Therefore, Pam did better on her test because her z-score is higher. She was more standard deviations above the mean. So that would mean a better test for Pam. And that is z-score.